on top as well. Yesterday I went through a whole thing.
Sean is preparing essentially the extension that goes to the upper grip, which will pull. Can you show that, just how it pulls? So that's the way it's going to pull. So this would be the left-hand side of the sample. And stop on that?
Yeah, it's gonna stop on its own. Hopefully.
All right. So he's putting the grip in. It's going to give a particular length. That length remains constant for the 3 left-hand side tests anyway. But it does give a angle that is not 90 degrees, so that's why we have to compare only the same geometries, unless we're going to do similar angles, which we will end up doing at some point. It's now elongating, and how many millimeters per minute?
I believe it's one
1 centimeter per minute, maybe?
per second.
Oh, 1 millimeter per second, okay. Okay, so you can see it's not quite a 90-degree angle. And that should mean that the force required to delaminate would be changing just as a function of the angle itself. And this one is decreasing slightly. Go. Now there's going to be a variation in these anyway. It's not like they have exactly the same curves. There's a difference in the adhesion. There's because of differences in how the adhesive was applied, or just weak spots, maybe a spot that had a drop of water. There's all kinds of things that can go wrong, so you integrate over the full curve, the force. And the force required is actually measured in or is reported in terms of newtons per inch. And the inch is the width of the strip that is being removed. So obviously the width times the full length of the material will give us the full area, and if we integrate force times distance over that full area, we get energy. And so 1 inch width times, say, 10 inches length gives us a certain amount of energy per 10 inches squared. So that would be the adhesive energy. So we have an adhesive force which acts over a length, and obviously the wider the sample, the more resistance there would be. So that's why we do per inch